Okay, just to double check, can everyone see the slides showing the iPad?
Yep.
Okay, thanks. Okay, let's just wait for perhaps one more minute, and then we'll get started. Okay, good afternoon, everyone. Let's get started. So first of all, apologize that I make a urgent decision to transition this lecture to be online due to the bad weather conditions and very bad road conditions within campus. I hope everyone is safe and convenient. Okay, so first, I just want to remind everyone, we got like 2 homework assignments left. The second last one, which is homework 4, has already been released this morning. So again, excuse me. If someone, would you please just mute? I heard some background music. Okay. Yeah, let me continue. So please start early. We got 2 weeks to finish that. The workload is not very high. It's just 3, I think it's 3 problems, a few smaller problems asking you to do some practicing of the Laplace approximation and the variational inference we discussed in the class. But again, if you need any help, please do not hesitate and just stop by the office hour, in my office hour or the TA's office hours. And we're gonna have another homework assignment, I think right after the deadline of homework 4. It will still take about 2 weeks, which is about Hamiltonian Monte Carlo sampling, which we're gonna discuss, and some Bayesian neural network stuff. Okay, any questions so far? Let me know if you have any questions or concerns or whatever. Just want to emphasize again, we don't have any final exam, so don't worry. You don't need to prepare for some exam, but we just request you to finish the remaining 2 homework assignments in time and also submit your final project report. We have given a deadline, so I know everyone maybe in the examining week will be super busy, but please do not forget the deadlines in our course. Okay, so let us continue with the Markov chain Monte Carlo sampling. So in the last lecture, we gave the very general introduction about idea of Markov chain Monte Carlo sampling, right? So you can view it as an alternative way to the approximate inference, like to the variational inference, to the Laplace approximation. So basically, our idea is the same, like given some probabilistic model like Z. Maybe I shouldn't use Z. Like theta and D is the observed data. Theta are the latent random variables, right? So you want to know what is the posterior distribution of your latent variables conditional on the observed data D, namely the posterior distribution, right? So usually it is analytical intractable, computational infeasible to get the exact form of this, right? So we got a Laplace approximation, which approximate this guy as an Gaussian distribution, right? And or we use variational inference and we maximize the lower bound to find the approximate distribution to get close to the true posterior distribution, right? But you have to restrict the approximate posterior distribution in a specific easy family, right? So the third idea is the topic we're discussing right now about Markov chain Monte Carlo sampling, which is essentially to construct a Markov chain. By simulating this chain, you expect that you can generate samples directly from the target posterior, right? So that's the idea, right? And so we introduced several like important properties of Markov chain. So here, there's something I want to highlight, like to avoid anyone like feel confused, right? So first, you can write a Markov chain, right? Visually, like a chain of the random variable z1, z2, z3, zn, blah blah blah. This chain can be infinite long, right? So each state zn represents the sample of n step when you simulate this Markov chain, right? And something we should be really clear is that the distribution of the state, right, of any state like z1, p of z1, p of z2, p of zn, they can vary, right? They can change, right? So meaning that, okay, in my sample, the initial state z1 arbitrarily say from Gaussian distribution, then you use some transition kernel. In other words, conditional distribution, you sample z2 given z1, right? You got a sample of z2, right? The distribution of z2 can vary. So just be careful, right? So when you simulate the Markov chain, actually the distribution of every state, namely every sample you generate, is varying. Okay? And ideally, we want, as you sample or simulate this chain for enough time. Sorry, the Siri just pop up. So your distribution of the sample, which is the n, when n goes to larger and larger, this distribution is getting closer and closer to the target posterior. Let me assume, no, let me redenote the latent random variable we're interested by, z, right? And Markov chain, a valid Markov chain, Monte Carlo algorithm guarantees that your chain, when n goes to infinity, in that you generate infinite number of examples, right? When it goes to infinity, then your distribution of your state in the chain will converge to the target posterior distribution. Right? That's the idea. And then our goal is to construct such a chain, such that the stationary distribution which this chain converges to is exactly the target posterior one. Right? That's the idea. Any questions so far? Okay, I assume everyone is happy at this time. Okay, so, and then the idea, I mean, the design of this algorithm actually is to design this chain. Like, how do we design this chain? So first, we want our transition kernel, like from any step, any state Zn, you generate next example Zn plus 1, which essentially is a conditional distribution of Zn plus 1 given Zn, right? We want to construct such a transition kernel so that the target posterior is invariant to this transition kernel, right? What does the invariant kernel, what is that? What does the invariant mean? Any thought? Any hint? Anyone giving me a guess? Okay. Is everyone not able to recall what we discussed in the last lecture? Okay. So invariant means just, okay, if your current state, say Z, N, is really sampled from your target posterior. Right? And then you use your transition kernel, right, which is a conditional distribution, to get the next state, Zn plus 1, to sample the next state. The distribution of your next state will also follow the exact posterior. Then we call this transition kernel is this target posterior is invariant to this transition kernel. So basically, you can imagine that, okay, you just simulate this chain, you know that the distribution of each state. Any question? The distribution of each state, we know that it is changing, right? It is varying along with the number of steps, right? And but at some specific point, right? If you change, if you have your distribution of the current state obeys the target posterior, then when you sample next state, Zn plus 1, the distribution of Zn plus 1 won't change anymore. It will still be the target posterior. So you can imagine that starting from Zn plus 1, you use the same transition kernel to generate next state, which is another sample, right? The distribution of that sample will still obey the target posterior. At that stage, that means you can keep running your chain, right? Because every new example you generated will be willed as samples from target posterior because the distribution doesn't change. That's why we call it this target posterior is invariant to this transition kernel because transition kernel doesn't change the distribution of new states. Any questions so far? Is everyone good? Okay, let me know. Any question? We do not want to get confused at those basic concepts. Otherwise, we won't be able to proceed to the more concrete algorithms. Okay. So another important property is that you need to ensure your chain is ergodic, which basically means that whenever initial state, whatever distribution you generate your initial state, right? As long as you run your chain, they will eventually converge to the same distribution. Then you don't need to worry about how to choose the initial distribution of your first state, right? So you can start from whatever distribution, you just sample your chain, just to simulate your chain enough long time, you found out, okay, this chain, the distribution of the state of this chain will eventually converge to the same distribution, which is our target posterior, right? That's why ergodicity is also very important, but practice, because it's fairly easy to construct ergodic chain, so we don't pay too much attention on that. And then the key question is how do we construct such a kernel, such a transition kernel, so that the target posterior is really invariant to this transition kernel, so that the target posterior will be really the stationary distribution of your Markov chain, right? So that means must have some way to justify that to test that your newly proposed transition kernel really can make your chain converges to that distribution, to the target posterior, right? So we mentioned that the most commonly used sufficient condition is called detail balance, right? So what is detail balance? Right? So let us take a look at the definition of detail balance, right? So basically means if we got two samples, right? Z and Z prime. If you can show that, okay, if you sample Z from your target posterior, then you sample Z prime conditional Z through your design kernel, this joint distribution, right, which will be Z and Z prime, is the same as you first sample Z prime from your target posterior, and then conditional Z prime and sample Z according to your transition kernel. This is another joint distribution which describes what is the probability you first sample Z prime and then sample Z. If these two joint probabilities are equal, then we claim that this P star target posterior is invariant to the transition kernel T. Okay, so we have given some proof showing that, which is pretty straightforward. But I do suggest everyone to try to prove this and strengthen your understanding about this detail balance condition. Any questions so far? Okay, so now let us keep all our current discussion in our mind. Like, let us look into some concrete algorithms. The first type of Markov chain Monte Carlo sampling algorithm is called the Metropolis-Hastings algorithm. So it's a very general, very broadly used framework for Markov chain Monte Carlo sampling. I would say like Metropolis-Hastings can be viewed as an umbrella of a large number of different Markov chain Monte Carlo sampling, right? So their design of the transition kernels can be viewed as special keys of the Metropolis-Hastings, and which satisfy the invariance, the detail balance. So, so what's the idea of the Metropolis-Hastings, right? How, more specifically, how does it generate every sample at each step in their chain, right? In each step, we're going to first use a proposal distribution. In the Metropolis-Hastings sampling, we need to first use a proposal distribution, right? Introduce a proposal distribution. We use a proposal distribution to generate a candidate example, given a current example, namely given a current state, CZN, right? We use a proposal distribution to generate a candidate. Then we're going to decide whether to accept this new sample. If we accept it, then we'll get a new state, right? If it's not accepted, we set this new state back to ZN. So this is called Metropolis-Hastings. So now let us look at in more detail, right? So let us denote the proposal distribution by this Q distribution. So we know it's a conditional distribution where conditional on the current sample, current state in your chain, right? So Zn, right? You want to get your sample Zn plus 1, right? But you're going to first use this proposal distribution to generate a sample Z prime, right? Here, let me emphasize this proposal distribution is not the transition kernel, it's just part of the transition kernel, right? Namely that you won't be able to directly use the sample proposal Z prime as your next state. You have to check that. And one commonly used proposal distribution would be condition Gaussian. Like for example, I condition the Zn, I give some variance and sample a proposal. So suppose we get such a proposal Z prime. Then we need to decide whether we're going to accept Z prime as our next state, Zn plus 1. And how can we check this, right? How can we determine whether we're going to accept Z prime? No. We use a probabilistic acceptance mechanism, right? So we use this probability to accept Z prime. So what's this probability? It's minimum between 1 and a fraction. Right? This fraction is the ratio between these two probabilities. Right? So let us look at the numerator first. Right? So the numerator in this fraction is that I'm going to evaluate the joint distribution of your model, right? And the data using this Z prime, your proposal, and multiply the conditional distribution, which is the proposal distribution of Zn give Z prime. right? So this is numerator. So the denominator is that, okay, I'm gonna evaluate the joint probability of your model again, but now I'm gonna take my latent variable to be the current sample Zn. And then multiply the conditional probability that given Zn, you sample Z prime using your proposal distribution. So it's like a starting from Zn, right? The denominator is like a starting from Zn, and Zn with the data D jointly obey the joint distribution, right? And then I jump to Z prime with my proposal distribution, right? So this probability, this product of these two terms are served as denominator, and then it will be divided by you starting from Z prime, right? And you assume you evaluate, okay, what is the joint distribution of your model with Z prime as your random variables value and data D, and then multiplying the probability that conditional Z prime, you generate Zn. So it's also like some kind of joint probability, you starting from Z prime, jump back to Zn, divided by the probability that start from Zn, you jump to Z prime. Then we'll look at this ratio and take a minimum between this ratio and 1 as your probability. Use that probability to accept Z prime. For example, this probability might be 0.8. That means you got 0.8 chance to accept the sample proposal Z prime. Otherwise, you're going to reject it. Any question? Is everyone comfortable about the definition? Everyone's good about this? Or is it super straightforward? Okay. So Nathan says, okay. Anyone else like feel uncomfortable about this? Okay, great. Yeah, I'm happy. I'm happy that everyone seems comfortable about this definition. Right? So as a practitioner, we know that we need to implement how to implement this probabilistic accepting procedure, right? So when we write a code of Metropolis Hastings, right? If you want to implement this accepting procedure, you can use one line of code. How do they see this, right? So you want to implement that you got this much probability to accept the newly generated proposal Z prime. You can sample a uniform random variable in 0 and 1, right? But then you just check your sample random variable if it is less than or equal to this guy. So I'm gonna ask, what is the right side of this guy? What is this guy? Any thought?
Term in the middle.
I see it again.
It's just the logarithm of all these terms.
Yes. Yes, exactly right. So you can see that the minimum is a logarithm and minimum and take exponential, right? So you can just move logarithm inside the mean. It doesn't matter, right? So it will be 0, and this guy will take a logarithm. That's where you see this, right? So log of the numerator terms subtracted by the log of the denominator terms, and that's it, right? And it's easy to check because you is a uniform distribution between 0 and 1. That means for the probability that u less than equal to anything, right? L will be just L, right? So, and here L will be this probability we just computed, right? So if we check, if you look at u to be less than all this probability, and it's just check and accept it, it just means that the probability that you accept this proposal is the designated probability. Okay, so if we accept z prime, right, meaning z prime passed the probabilistic check, we're gonna set our next state to be z prime, the new sample generated from our proposal distribution. Otherwise, we're gonna set our next state to be the current state, Cn. So you can consider that when you simulate this chain, right, because in many cases, even you generate new examples, it might be rejected, right? And then you have to duplicate the previous example as your next state. So the chain may contain many duplicated samples due to rejections. And through this rejection, we can also see that if your newly generated proposal Z prime happens to be rejected, you actually do not generate any new sample, right? That means you actually waste the computation from sampling from the proposal distribution, right? So this is actually a big problem, right? You don't want so many generated examples to be proposals to be rejected, because once you reject them, they don't bring new examples. They're just wasted. The computational cost just wasted. We're going to walk into this problem later. Okay, so before we talk about the guarantees of metropolistic, any questions so far for this whole procedure? Okay, so next we're going to talk about why doing this is correct, right? Why we break the transition kernel into two parts. Like first, you use an arbitrary proposal distribution, and second, you do some acceptance test, probabilistic acceptance test. Will give you a valid chain. Here, valid chain means that your target posterior will guarantee to be the stationary distribution which your chain converges to. Okay. So you can show that the Metropolis-Hastings framework guarantees the detail balance, right? As we mentioned, if your chain satisfies detail balance, that means your target posterior will be invariant to your transition kernel. That means your chain will converge to the target posterior eventually, right? So suppose you got two consecutive states, for examples, generated by your chain simulated through this Metropolis-Hastings algorithm, right? We did them by Zn and Zn plus 1. So let us first consider the case where these two examples are different. Like Zn plus 1 is not equal to Zn. Right? In this case, we know that this state Zn plus 1, like, must be obtained from accepting the proposal. Right? Otherwise, we know that if it's rejected, we have to set Zn plus 1 equals to Zn, right? Then Zn plus 1 cannot be right, cannot be different from Zn, right? So so in the case that if Zn plus 1 is known to be different from Zn, we know, okay, Zn plus 1 must be generated a new proposal and get accepted. So let us check what is the transition kernel, or what is the conditional probability from Zn to generate Zn plus 1, right? So as we mentioned, right, the transition kernel actually consists of two parts. First, we're gonna use the proposal distribution to generate a proposal, right? Which we denote by Q, which is conditional probability of Zn plus 1 gives Zn. Then, because Zn plus 1 is accepted, right? That means the probability n plus 1 is accepted is this mean of 1 and this fraction. Right? And then let us look into this fraction. Right? If we divide both the numerator and the denominator, right, by this marginal distribution of the data d, right, it doesn't matter because they're dividing both numerator and denominator are dividing by the same constant, right? So you can see that the joint probability of Zn plus 1 d divided by P of d will be the posterior distribution of Zn plus 1 given d, right? Similarly, in the denominator, the joint distribution of Zn and d divided by the marginal distribution of d will be the posterior distribution of Zn given d, right? And then we multiply with this conditional proposal distribution, right? This is our transition kernel, right? So we know that to test the detailed balance, right, we need to check that, okay, if we, so this is Zn, right, generate Zn plus 1, right? So we need to look at if Zn is really generated from the true posterior, right? And then condition Zn, you generate Zn plus 1. What is about this joint distribution, right? Joint distribution to sample Zn first according to the true posterior, and then condition Zn, you generate Zn plus 1. And that means you just sample, you just multiply this joint distribution, just multiply the true posterior of the little random variables taken Zn, and then multiplying this transition kernel, right? And now we look at the product of the probabilities outside of this mean, you see that it's the same as the denominator in the fraction part, right? And then if you just, because this product must be non-negative, right? Must be positive, so you can just multiply them into the mean, it doesn't change the mean. So eventually you'll find that this joint probability equals to mean of the denominator part and the numerator part in this fraction, right? Because the denominator part is the same as the part outside of the mean, right? If you multiply in, you're gonna have this cancel out, and then you multiply 1 with this, right? Does it make sense? Okay. And now we can check on the other side, like if we generate Zn plus 1 first, right, through the exact posterior, right? Then condition Zn plus 1 to generate Zn with the same procedure, right? So what is this joint probability? Can anyone tell me how to do that? How to compute that? Any thought? You actually do not need to figure out what is the proposal distribution, what is the acceptance probability, all kind of stuff, right? You can just switch Z and Z plus 1 in your computed results, right? Just switch the index, right? You change n to be n plus 1, you change n plus 1 to be n, and that's it, because it kind of follow the same computational procedure, right? The only difference is index of the variables. If we doing so, we find out, okay, if you just sweep Z and Z plus 1, and inside this mean, you actually just exchange the left and the right part. it won't give you any difference about the mean value of the left item, the right item. So they're exactly the same. Any questions so far? Is everyone happy with this reasoning? Okay. Okay. So the next part, we just need to talk about a very just a corner case where what if Zn plus 1 equals to Zn? So meaning that your state at n plus 1 is exactly the same as the state of step n, right? So if that happens, there are two possible cases, right? One case is that you got some new proposal, but it was rejected, right? And the second case is that, okay, your new proposal actually is exactly the same as Zn, right? Although it's kind of like rare, but it is not impossible, right? So if you sample some distribution, Zn, conditional Zn, and it happens to sample the new example, I mean, from some proposal distribution, you sample a new proposal, exactly the same as Zn. It is not like impossible, although it is rare. Right? So we just need to look at the two cases, right? So the transition kernel, namely the conditional probability of Zn plus 1 given Zn, right, is now can be represented as summation of two probabilities. First, you generate some kind of proposal, you got rejected, right? Second, you got a proposal, Zn plus 1, which is exactly the same as Zn, and it got accepted, right? And we actually do not really need to compute what exactly the form of each of these two probabilities, right? We just put these two parts together and let us try to analyze the detailed balance, right? So first, if we consider Zn, so Zn plus 1, right? So starting from Zn, and Zn is supposed to be generated from the target posterior, and then you multiply the transition kernel, right? You got the joint distribution of Zn and Zn plus 1. Here, Zn plus 1 is exactly the same as Zn, right? It is this distribution, the target posterior of distribution where your random variable takes Zn, right? Multiplying with this guy, right? You reject the proposal plus the proposal is Zn plus 1, get accepted. And on the other hand, you need to check that, okay, what if you start from Zn plus 1 and then suppose Zn plus 1 is first generated from target posterior and then you jump back to Zn again, and Zn now is still exactly the same as Zn plus 1, Zn plus 1, right? So your transition kernel, right? So this product essentially is the target posterior when evaluated as Zn plus 1, right? But Zn plus 1 equal to Zn, so it's the same probability density, multiplying with this conditional probability. This is transition kernel, right? Zn given Zn plus 1, right? So, however, because Zn and the Zn plus 1 are exactly the same. So the first part that you're starting from, you condition on Zn is the same as you condition on Zn plus 1, right? Then you generate some new proposal and got rejected. This whole probability is the same, no matter you start from Zn and Zn plus 1, because Zn plus 1, the conditional part is exactly the same. And the second part is that, okay, your Zn, your conditional Zn, your proposal Zn plus 1, you get accepted, right? It is the same as you conditional Zn plus 1, you get Zn, the proposal accepted. Why? Because Zn plus 1 is the same. So basically, these two conditional probabilities, right, two transition kernel values, they are exactly the same. And because they are multiplying with the same posterior probability. So overall, these two products are the same. Any question? Okay, so now we have a finished discussion of the two cases, right? We can see that in both cases, like no matter if your next state is exactly the same as the previous state, or is the same as is not exactly the same as the previous state. In both cases, your chain satisfies the detail balance. That means the target posterior will be your stationary distribution, right? Your chain will guarantee to converge to the target posterior. So this is a valid chain. Okay. So in practice, right, to implement a very easy, convenient Markov chain Mitchell-Hastings algorithm, often used proposal distribution is a symmetric proposal distribution. For example, a Gaussian distribution. Suppose I want to start from Zn, conditional Zn. I want to generate a new proposal. I can use a conditional Gaussian, which is conditional Zn as a mean, and you got some variance to allow some new examples surrounding Zn that are generated. Right? So if we use such a symmetric proposal distribution, we can take a look at acceptance probability. Right? So the minimum of this 1 and fraction. Right? So we know that in a fraction, both the numerator and denominator contains the proposal distribution conditional Z prime to generate Zn, and the proposal distribution conditional Zn to generate Z prime, right? Because they're symmetric, that means you can switch Z prime to Zn. They are the same, like this Gaussian. So they're canceled out. That means your acceptance probability is really the minimum between 1 and the fraction between the joint probabilities evaluated at your new proposal Z prime and the current state, the current example Zn. Okay. So if you use such a symmetric proposal distribution, then we call this algorithm a Metropolis algorithm. Any question? Okay, so a more interesting observation is that, okay, if you use symmetric proposal distribution, you do some Metropolis sampling, right? It's not Metropolis-Hastings, Metropolis sampling. We find that if your new proposal can increase the joint distribution, namely, you evaluate your joint distribution as Z prime. If it's bigger than you evaluate your joint distribution at current sample Zn, then we know this fraction must be bigger than 1, right? The minimum of 1 and a bigger than 1 value will be 1. That means you have 100% chance to accept the new proposal Z prime. It implies that if your sample proposal will increase the model probability, then this new proposal will always get accepted. Right? Like, for example, if this is your target posterior, right? So if this is your current example, Zn, right? And suppose you have some symmetric Gaussian to generate new proposal, right? If you generate a proposal here, then your acceptance, your joint probability evaluated at Z prime here, right? Actually decrease the joint probability is less than 1, so you have a certain chance to get rejected, right? However, if you generate proposal Z prime at here, right, where you kind of increase the joint probability of your model, then Z prime will definitely be accepted as your new sample. Any question? Okay, so so it looks like Metropolis Hastings algorithm is very generic, right? You are free to choose arbitrary proposal distribution to generate examples, right? And also and using Metropolis algorithms is even convenient because if they choose symmetric proposal distribution, right? I mean, it's the proposal distribution or proposal density just cancel out just to look at if your generated a new example can really increase the joint probability. If it increases, it must get accepted. Right? It seems pretty straightforward to implement. However, in practice, people really, rarely use this type of method, like you construct some symmetric proposal distribution and do this. And why? Because that will make your sampling procedure to exhibit a severe random walk behavior. And if you perform random walk, implies that a lot of computational costs will be wasted. You won't be able to get a large number of effective examples unless you consume a huge amount of computational resources. So what does it mean, right? So let me first read this detailed explanation and then give some concrete example to explain, right? So why we do not like to use symmetric proposal, right? That's because we need to collect samples that fit the target posterior. So meaning that the histogram of your collected samples should be more and more like the posterior, right? So that means mining samples should be on the high density region of the target posterior and much less sparse examples are on low density regions. However, if you generate proposals like random walk, meaning that you just shoot everywhere, just produce everywhere, and due to the requirement, right? Due to the requirement, we can only preserve examples with higher chance in high density regions, right? In many other places, the low density regions, that means you're gonna waste a lot of generated examples, generated proposals to collect the collection of examples that we really want. How do we see this more concretely? Like, for example, this one is our target posterior, right? So if we want to generate good posterior samples, what does it mean? It means that, okay, you're gonna have many samples in high density regions, which will be here, right? Right. You might have like much dense. You might have much more examples in high density regions, right? And but here and here, low density region, it's pretty sparse, right? Maybe here, we're gonna have dense examples, right? And if you just draw a histogram, right? The histogram will show, okay, the frequency of examples showing in this high density region will be high, right? And frequency of examples that show in the low density regions relatively low. So your histogram will be very low, right? Here, something like this, right? Does it make sense? However, we'll propose a sample, right? We'll propose the sample. You don't know which places you should generate more samples, right? With generate proposals, you especially use symmetric proposals, you actually randomly generate a proposal in any direction, right? You got the same chance to generate samples here, you got the same chance to generate samples here, right? Use, right? So that means you might have a 50% chance in this case, generate samples that should be allocated high density regions. And you also, at the same time, you also generate same number of the examples at low density regions. And then we know that to get the target proportion of those samples, the proposals you generated at the low density regions will be largely rejected. That means that those large number of proposals are totally wasted. The computation cost was wasted. Does it make sense? Any question? So let me add a little another example before I ask your before I wait for your questions, right? So it's like your eyes are covered, okay? And you just random shoot, right? So the targets, right? The targets. So this is a circle, right? So you are the person, right? You're a person here, right? The targets is only one direction, which you do not know, right? And you only want your bullets on the targets, right? Which correspond to high density regions, right? However, your eyes are covered. You do not know which direction is the right direction. What do you need to what are you going to do, right? Using symmetric proposals, you just blindly shoot in every direction, right? And perhaps you shoot 100 bullets. There are only one bullet hit on targets. Like all the other bullets, like 99 bullets, are just wasted. Right? And our goal is that, okay, on this target, we might need 100 bullets. That means corresponding to the target posterior. I mean, the high density regions, I might need 100 samples, right? However, because you're blindly shooting, right? If you just every time you shoot 100 times, you got one bullet hit on target, right? If you want 100 bullets hit on target, you have to shoot for 10,000 bullets, right? 99% of the bullets are just wasted in order to get 100 bullets right on target. That's the problem of the random walk behavior, because they're trying to generate samples blindly. And unfortunately, because the high density region is very few in the whole space, right? Most of those proposals will be just rejected. Okay, any questions so far? Any thought? Is everyone good? Everyone's comfortable? Okay. Okay, thanks. Yeah, hopefully this illustration can give you an intuition why Metropolis algorithm or simply design like symmetric proposal is not very popular in practice, because it really wastes too much cost, and the generation of the proposals are so inefficient because most of them will be just rejected. Okay, then how do we address this problem? Like, so next we're going to introduce two very widely used sampling algorithms. One is called Gibbs sampling, the other is called hybrid Monte Carlo sampling. Both methods can effectively address this random walk behavior. So you see that Gibbs sampling, the acceptance rate is always 1, meaning that you won't waste proposals. And for hybrid Monte Carlo sampling, you see that it can guarantee a very high acceptance rate. But it also, but at the same time, it addresses some problem of sampling, because sampling, you'll see that although the acceptance rate is 1, but due to the correlation between the random variables, it cannot very efficiently explore the whole sample space. That's their problem. Okay, we're going to start with the Gibbs sampling. Gibbs sampling overall can be viewed as a special type of metropolis testing algorithm. However, it very smartly designs the transition kernel. So it uses the conditional distribution to sample each single random variable, given all the other random variables in your model fixed, and given the data fixed. Right? And by using this transition kernel, the conditional distribution, the acceptance rate is always 1. It's guaranteed to be 1. I will see that later. Okay. However, the precondition of using Gibbs sampling is that you can guarantee your conditional distribution is tractable and it's easy to compute. Otherwise, you won't be able to use Gibbs sampling. Okay, let's see. What's the details? What are the details of Gibbs sampling? Suppose this is our latent random variable z, right? So we got latent random variable z, and given z, you sample the data d, right? And z, we assume it contains m elements, z1 to zm, right? So your joint distribution of z and d can be written as a joint distribution of z1 to zm and zd, right? So the Gibbs sampling is performed as follows. First, we're going to assume for each element in Z, like say Zi, condition on Z not I, meaning all the other variables in Z other than Zi, and condition on the data D, this is tractable and easy to sample. And then we're going to sequentially sample every element in Z to get new samples according to this condition distribution. Specifically, right, suppose we initialize our Z random variable, which is vector, right? So the sample of each element is Z11 to Zm1, right? And then in each iteration, right, first, we're going to condition on all the current Z samples except Z1, right? The condition on Z2n, Z3n, Zmn, and condition on data D, we generate a sample for Z1, which we denoted by Z1 plus 1, meaning a new sample of Z1. And next, we're going to condition on this new sample of Z1, Z1 plus 1, Z1 plus 1, right? And all the other samples of Z2 or Z3 to Zm, right? So we know that right now, Z3 to Zm, they're still the current samples, right? There's no new samples, right? We condition on Z1 new sample and all samples of Z3 to Zm, and condition data D to generate a new sample for Z2, the second element. So we get a new sample for Z2. So we denote it by Z2 and plus 1. So in the third step, we're going to condition on new sample of Z1 and Z2, and also all the other samples other than Z3, right? Will be Z4 to Zm, and at the current samples, we generate new sample for Z3. So you can see that every step, we're going to use all the current samples of all the other random variables to generate a new sample of the current random variable until we generate the new sample of the last element in Z, condition on Z1 to Zm minus 1. So in this way, you can see that after m steps, we actually can generate a new sample for every element in Z, so we get the next state of Z. We finish the one iteration, right? And then we just go through this cyclic procedure to generate a new sample of every element in Z again in the next step. Right? We keep doing that. And a question regarding this procedure? Everyone's clear? Okay, that's great, right? So, but still, I want to use some concrete example to showcase how this is working, right? So suppose I am only equals to 3, that means only Z only contains 3 elements, right? At the beginning, I'm going to initialize Z, right? Z vector, we call Z1 to be like 0.1, 0.2, 0.3, right? So in each iteration, right, we're going to first condition on Z2 and Z3 to sample a new element for Z1. So Z1 is sampled from the conditional distribution, which is conditional on Z2 equals to 0.2, Z3 equals to 0.3, and of course data, right? So you got a new sample for Z1, which we denote by Z12, right? So suppose this sample is 0.4, right? So I got new vector, which is 0.4, 0.2, 0.3, right? And next, we're going to generate a new sample for Z2. How do we do that? We're going to condition on the other 2 variables, right? So we're going to sample the next variable of Z2, right? From this conditional distribution, conditional the current sample of Z1, which is 0.4, right? And the current sample for Z3, which is still the old sample, 0.3, and given data D. Right? And suppose, let me just blindly write down some numbers. Suppose this generated value is 0.15, right? So now I got my state vector to be 0.4, 0.15, 0.3, right? So we know that 0.4 and 0.15 are new samples for Z1 and Z2, right? So then in the third step, we're going to update the sample for Z3. How can we do that? We just look at the conditional distribution of Z3, given that Z1 is the current sample, which is 0.4, Z2 is current sample, which is 0.15, right? And of course, given the observed data D, we got a sample of Z3, right? And suppose this guy is minus 0.1, right? And then we get our state vector to be 0.4, 0.15, and minus 0.1. So we see that every element in Z has been updated to a new sample. So we finish one iteration, we get our Z vector sample in the next step, right? And then we just continue to do this, right? Conditional Z2, every element in Z2 is sequentially get new sample of every element in Z and to get Z3, right? We just keep doing that until the burn-in stage has arrived, and then we just take out every, say, 5th examples or 10th examples to form our collection of the posterior samples. Okay. Any questions so far? Okay. In practice, it's not necessary for us to do every element wise. Like I'm gonna sample first element, conditional on the other elements, and then sample the second element, conditional on the other elements. We can further partition the random variables into subvectors. Like say this Z is 100 dimensional. I can partition them into 10 subvectors. Each subvector is 10 dimensional. So then this alternating sampling procedure is that, okay, I sample ith subvector conditional on all the other subvectors, right? Then we can still do this alternating sampling to generate the new sample of each subvector. Then we put them all together, we get a new sample of the whole Z vector. And this is called blocks. A block gives something. In practice, you can always like find a smart partition of your random variables into several blocks. Okay, so Next, we're going to use a concrete example to show why keep something can be very convenient. Right? So we use a example is called model is called matrix factorization. Right? So matrix factorization is a fundamental algorithm in modern recommendation system, like in Netflix, in Amazon, in Google, like and we know that when we rate movies in Netflix and leave comments, all kinds of stuff, Netflix try to collect those data and trying to recommend you a set of new movies you might have never seen, right? They guess that you're gonna like them, you're gonna keep your subscription, right? Similarly, for Amazon, they keep recommending, suggesting new products and trying to consume, exhaust their wallets, right? That's their main way of trick to earning money from you, right? So all those stuff can be reduced to a so-called matrix factorization problem, right? So we got a set of users, we got a set of movies, right? So we can form a rating matrix where each entry, the value in each entry represents the rating for a particular user to a particular movie, right? Say here, it just means user 1 rate movie 2 as 1.2, and here means user 3 rates movie 3 as 4.3, right? But of course, this matrix can be sparse because a user cannot usually has watched like 10,000 or 20,000 movies, right? They only watch like 10 movies and they leave 10 ratings, but this whole matrix can be very large. Right? Then the idea of matrix factorization is to represent, to learn some kind of representation, right? Or sometimes it's called embedding, to represent each user. You can view it as a latent feature vector, right? Then according to the feature vector, they want to predict what is the missing entry values. If you're able to predict the missing entry values, you're able to predict those rating that user for those unseen movies, right? And then you can, according to your prediction, to suggest movies or recommend movies, right? You can, according to your prediction, you can recommend movies which, according to prediction, is high. Right? So this is the setting. Any question? So in the Bayesian framework, how do we formulate this matrix factorization problem, right? So first, for each user I, we're going to introduce a k-dimensional latent feature vector, which we denote by UI, right? This is something we want to learn from data, right? And for each movie G, we introduce another k-dimensional latent feature vector, which we denote by VG. And then we first assign some prior over the latent feature vector for every user and for every movie, which for convenience, we just use a Gaussian distribution, right? Standard Gaussian distribution. That means the prior probability of each representation feature vector is just a standard normal distribution, right? And then you can stack all the users feature vectors into a matrix, right? See, you can define a user matrix as U1 transpose to UN transpose. Suppose you got N users, right? Similarly, you got a feature vector matrix, a feature matrix for movies can be V1 transpose, see Vn transpose, right? You just stack all those feature vectors together, right? Then, given your feature matrix of U and the feature matrix V, right? And we sample each observed rating, right? Say the rating for user I on movie G is sampled from a Gaussian distribution where the mean is the dot product or inner product between UI and VG, and variance is tau. So this is our Bayesian version of matrix factorization. And then we can write down the joint probability, right? So this is the prior of the feature representation for every user and for every movie. And this is the likelihood, right? This is all represent all the observed ratings, right? So for each observed rating, the likelihood is a Gaussian distribution, where the mean is the dot product between the corresponding user's vector, feature vector, and corresponding movie's latent feature vector with variance tau. Okay? And our goal essentially is to estimate the posterior distribution of your user feature vectors and the movie feature vectors given the observed ratings, right? Any questions so far? Is everyone clear about this model definition? Everyone's good? Okay, now I want to claim, although every term in this Gaussian distribution, in this drawing distribution is just Gaussian terms. So we know that this guy is just a standard Gaussian, right? This guy is a standard Gaussian, and this guy is also a Gaussian, right? It's Rij. Let me write it in a nice way. Okay. My claim is that you compute the posterior distribution of all the latent user feature vectors, latent movie feature vectors is analytically intractable. You won't be able to compute it as a closed form. Why? Any thought? Why? What causes the intractability in computing posterior distribution? Yeah, thanks, David. David said it's Gaussian multiplied together. Yeah, you're right. Gaussian multiplied together, not necessarily Gaussian. So the K problem comes from here. This dot product. To see this, right? Let us assume, okay, you only have one user, you only have one movie, right? So that means your drawing distribution will simply say U1 and 0i, like this standard normal prior, right? U1, 0i. Suppose you'll get one rating, which is just R11 given U1 transpose V1 and tau, right? Suppose tau is known, like you know this variance. Right? So now if you want to compute the posterior distribution of U1 given R11 or V1 given R11, my claim is that you won't be able to compute. The reason is that you multiply two Gaussian vectors altogether, then you can now say, you integrate them together, your U1 given R11 will be Gaussian. It's not Gaussian. You can try this, right? You can even try to, like, for example, if you want to compute U1, V1 given R11, right? It is equal to the joint distribution which is just those product, right? Divided by P R11, right? So that means you have to marginalize out U1, V1 in this joint distribution, right? So you just need to integrate this with U1, V1. You see that you are now not able to integrate because this guy will make you very hard. Again, I suggest you to try that. Right? Okay, and then how should we do that? Right? How should we address this inference problem? Right? We're gonna use a Gibbs sampling. Right? So, although for the joint distribution, if we look at what is the posterior of UI and VG conditional data, right? Because it's product, because it's dot product, right? you won't be able to find analytical for that. Right? But if you use Gibbs sampling, if you condition on, say, VG, you look at the condition distribution of UI, you see that it is Gaussian. That's a very interesting observation, right? How can we see that, right? We can take a look, right? So again, let us look at a simple case where you only have one user and one movie, right? So you got your drawing distribution to be the prior of U1 and the prior of V1. You only have one likelihood, R11 and U1 transpose V1 and tau, right? So we're looking at U1 given V1 and given R11. R11, remember, is our data. Right? So this will be a Gaussian. Why? Because you're conditional on V1, right? So V1, now when it's conditional, you can view it as a known constant, right? So that means in each term here, right? In each term that contains U1, right? There's just a Gaussian with U1's linear transformation. If you look at your exponential term, it will be something like this, right? Half tau, like V R11 subtracted by U1 transpose V1 squared, right? So if you expand this term, you will see that there are just linear terms about U1 and quadratic about U1, and combined with the Gaussian term, Gaussian prior of U1, which is also a linear term of U1 and quadratic term U1, you merge them all together, you will still have your exponential to be some linear term of U1 plus some quadratic term with U1, which is simply Gaussian. So that means your conditional distribution of U1 is, see, it is mu1 and sigma 1. It's very easy to sample and very easy to compute, right? Because it's just sample from a Gaussian, right? Once you sample, you generate sample for U1, and if you look at the conditional distribution of V1, given U1 and data R11, it is still a Gaussian, right? Because it's symmetric, right? You condition on U1, and then the Gaussian likelihood is just contains the linear transformation of V1, right? So you merge the term, the prior term of V1, you still get a Gaussian. That means the condition distribution of V1 given U1 and R1 is another Gaussian, right? See M1 and lambda 1, right? And it is very easy to sample V1 according to this Gaussian form, right? Then you can do this alternating sampling for U1 and V1. And the same argument applies to the joint distribution. The only difference is that, okay, you have multiple U vectors, multiple V vectors, but when you sample U vectors, right, say UI, you just need to look at and condition on all the other U vectors and V vectors, right? Conditional data. You just need to look at the prior of UI and all the likelihood that contains UI, because the one who do the dot product with UI is conditioned, is fixed. So they're just a linear transformation of UI. So you can merge all of them together, it still be a Gaussian, right? And it's very easy to generate a sample for UI, right? And similar, the same argument applies to the sampling of every VI. Then you're doing Gibbs sampling is very convenient. Any question? Is everyone comfortable? Okay, again, I highly encourage everyone, right? If you capture the convenience of running Gibbs sampling for this matrix factorization example, please sit down for 10 minutes and try to derive the conditional distribution required to generate every sample at each step, and you will have an even better understanding. Okay, thanks. let's stop here and see you on Thursday. And I hope we'll meet in person.